Anyway. Hello, folks. Welcome to Rational Science. Finally, we got our equipment working. I hope everything's okay. I hope you can hear me fine.
Finally got a good laptop.
Please let me know if you're receiving signal, sound, video, the whole works, okay? Okay, if someone would confirm, you can look it up there as well. Yeah,
Sure.
Yeah.
Yes, headphones.
Okay. Yeah. Okay, so let's get started. We had a little bit of problems yesterday, technical problems. But the good news for me, at least, is after 2 months. Okay, thank you. After 2 months, I found my son. Hans, I don't know where, but we found him.
In the middle of a desert.
Yeah, and did you start that war in Israel?
Yeah.
Because just as soon as you left,
That
the
was
war
me, guys.
started.
That was me, guys.
Okay, just
Watch
wondering.
out.
Okay, anyways, we got a great show today. We're going to be talking about what? Dark energy.
Why are we talking about dark energy?
I have no idea why, but that's what we're going to talk about. Well, because we're on a roll talking about the universe. Lately, we've been talking about the universe for 2 months, different aspects of it, relativity and so
There's a
on.
lot to talk about.
Yeah, there
Even
is.
beyond relativity, if we're talking about actual universe.
Yeah,
complicated.
and the big problem that we have out there is language. Language. A lot of people think that anyone who does language, does clarification of language, is doing word wizardry, word salad, semantics.
Minor stuff, wasting their time.
Yeah. It's like for them, it's just noise coming in the ear and coming out the other. So what we do, we start with, and I'm going to be starting today with some of the questions and comments people made, because that's going to lead into the subject matter of today. So I'm going to work it in reverse. Instead of answering the questions at the end, today we're going to start by answering questions that people asked, because they're related to the subject matter of today. Okay. So let me start with this. What we do in this channel, we like to put what is known as the universal movie.
I do have to say before we start, I like that when I look up rational science, this is the first thing that shows up.
What?
We're the only people doing rational science.
Oh yeah, that's. Anyways,
Okay, let's go.
here we have the universal movie, and what it is, you have to imagine the universe. Every atom in the universe has location. That's all it has. Okay. And in the next microsecond, billionth of a second, quadrillionth of a second, every atom in the universe is at a different location. So everything moves from location to location to location. And in one of those frames, all we have is location of every object in the universe. So think of that as a 3D movie. And one of the problems we have is that a lot of people, especially dissidents, they use concepts as physical objects, specifically the ones that I circled there: plasma and ether. The establishment also uses field, but those are the three words that are always used as physical objects.
Well, the thing that the concept that's used the most as a physical object would have to be motion. Movement is moved.
Indirectly.
Indirectly, movement is moved the most.
Yeah, if you say to people, is motion a physical object, they'll say no. But if you say, is plasma, ether, field, or energy a physical object, well, people have problems with that. They think these are physical objects. And as you can see, I put them at the bottom because those concepts are dynamic concepts. They take at least 2 frames of the universal movie. Whereas the ones on the top in yellow, they only occupy 1 frame of the universal movie. Okay, so that's essentially what we're trying to show there. And what we'll see today is some of the questions that I'm going to be answering today are related to dynamic concepts, which people treat as physical objects. That's the whole problem. Okay, so it is a language problem. And again, for them, it's just noise in their ear. They say, well, I came here to do physics, not grammar.
Yeah.
We have to do physics is 150% semantics.
I wish it weren't, but
you gotta define your terms. You gotta tell us what you mean by the words.
it's not really, but it has become that way. since people have abused it for so long, now it's become the first thing that you look at.
Absolutely.
It's just because due to the abuse of the English language,
English and any
language that is done in.
And it's important to note that mathematics is only a language. I mean, people say, well, the language of physics is mathematics. Well, is the language of physics Chinese? Is the language of physics Greek? You know, it's Greek to me, and so that's the language of physics. No, the language of physics is illustration if you're going to be explaining a mechanism. Okay, so we got to keep that in mind. So one fellow says the following. Let's get started here. He says the following. He says, seems unfair your definition of plasma. Right? Plasma is a highly ionized gas. And then next slide, you define ionization. Okay, ionized is past tense. Okay. It's already ionized, finished, like he imagines it. If chemical reactions are occurring in air, it doesn't make it any less of a gas. Okay. So what is this fellow saying? Well, he's saying essentially this. He's saying, look, here we have ionized gas or ionized atoms on the left-hand side. You take a snapshot of it, which is the one you see on the right-hand side, right? And he says, well, it's already ionized. The one on the right is already ionized, ED, finished. And the question is, if I take a snapshot of ionized gas, ionized atoms, can we say that plasma is a static concept because I was able to put it in a snapshot? Okay, so that's the question. And the answer is no. Because the word plasma already embodies motion. Let me repeat that because I don't think that's sunk in so easily. The word plasma already embodies motion. And what we should be doing is really maybe defining plasma so that these people understand is instead of ionized atoms, we should be calling them constantly ionizing atoms because they're constantly being ionized. Plasma never stands still because if it does, all the electrons recombine with their atoms. And so, and it turns into gas. So we cannot stop the word plasma. What this person is trying to take a picture of is not atoms or gas. He's trying to take a picture of ionized or ionizing. And you can't. That requires 2 frames of the movie. And here, let me
is it because you have to have the atoms with the ion and then without it?
No, the issue is that plasma is a mixture, right, of atoms together with normal atoms that have not been ionized, that have not lost their electrons, right, together with other atoms that have lost their electrons. If we're going with a quantum mechanics version, which is really the one these people have in mind. So some atoms have lost their electrons, some atoms have not. And it's a soup, it's a mixture. Something is stimulating that ionization constantly.
But if someone took a picture of has already lost its electron ionized gas, they have a picture of just the part where where the electron is out.
Yeah. I hear you. I understand. Right? Yeah. Now what?
Can you point to that and say that's plasma?
No, because the word plasma means ionized, not gas. It means ionized, and you're trying to take a picture of a verb.
That's
so
it's like a fine line.
Well, no, here. So here we can see it. I think you'll understand what my argument is. What semantics, word wizardry, word salad. Okay, here's a little word salad for you. Okay, here we have it. On the left-hand side, we see a running boy.
Yeah.
Okay? That's a movie. I went in a single...
They can see it now.
Okay, on the right side, you have a boy. And you say, well, I took a picture of a running boy.
Yeah.
No, you haven't taken a picture of running. You took a picture of boy. Okay? Running requires... You can't take a picture of running because running always requires 2 frames of the movie.
Ionized gas is still just gas?
Well, it's ionized. You're trying to take a picture of ionized. You're trying to take a picture of running.
But if you were to take a picture of ionized gas, you'd say that it's just gas because you're trying to add the running. to the gas.
Yeah, because you're really not taking a picture of gas itself, because it's not, the question is not whether you took a picture of gas. You took a picture of what is known as plasma, but the word plasma has that adjective in front of it. It's called ionized or ionizing.
But if someone brought a picture of plasma to you, it would be as if it were the boy that were in one frame running. You would say it's just gas.
You could say that, but even there, you would need to have a comparison to, without the ionization.
No, you don't care. You don't need.
No. What I'm saying is, if you try to explain it to an ET, right, and you say, look, there's a bunch of little balls there, and then smaller balls, which are the electrons, are out. He won't know what he's looking at. He's looking at a bunch of balls. That's all it is, really, for him.
He'd just say it's gas, right?
Yeah, at best he would say it's a gas or just a bunch of balls. Yeah. You would have to explain to him what it is. But my point here is another one. My point is that you're trying to take a picture of a verb. You're trying to take a picture of running. You're trying to take a picture of ionizing.
Well, you said something interesting yesterday that I still was trying to wrap my head around.
The adjective?
Yeah, you said that physics, and I don't know if everyone here agrees with this. Let's see if we get a show of hands. Physics, I don't know how you phrased it, but something like does not require or does not need adjectives.
Yeah, you can't use, there's no such thing as a dead cat, like in Schrodinger's cat, right? There's no such thing as a live cat. There's no such thing as a green tree, as a brown house. There's only a thing called house.
Superfluous poetry is that what adjectives have become.
You cannot put an adjective in front of a noun for the purposes of physics. In physics, we point to an object and we don't say it's the greenhouse. No such thing as a greenhouse. There's only such thing as a house. Green is an adjective, and now you're qualifying it. You're comparing it against brown, blue, and other types of houses. So you're making a comparison. If you just want to point to the object, you say house, cat, dog.
So you're saying if this were a court of law, that'd be grounds for an objection. Objection used an adjective. But you said adverbs are fair game?
Yeah, well, I'm saying adjectives do not come together with nouns in physics. In physics, you point to the noun, to the cat, to the dog, to the rock, to the tree, to the house. You point, and say chair. You don't say that's the brown chair. No such thing as a brown chair in physics.
But
now,
it
as an object.
Is it because we don't care? Is it always unnecessary information? Does it just muddy the water?
It muddies the water.
Are you adding motion? What are we doing here?
Well, people will say, well, I can take a picture of ionizing atoms or ionizing gas. No, you don't realize it. You're trying to take a picture of ionizing, not of the gas or the atom.
Yeah.
Okay, and here it is. This is the definition. Now, there you have it. Plasma. Constantly ionizing atoms. I don't know how else to define it so that people don't try to work around it. If it's constantly ionizing, you can't take a picture of that, because as soon as you take a picture of that, you don't have plasma. What you try to do is take a picture of ionizing, and you cannot remove the word ionizing from the word plasma. That's the issue.
We have someone that says constantly balding head. Balding is a process. You can't just point to a bald head because he's balding.
Yeah.
I think he's talking about you.
Okay, yeah. There. Okay, and here's another aspect to our good old plasma, okay? A lot of people say, well, Bill, it's a state of matter.
Mm-hmm.
No.
No.
Absolutely not. Let me show you why. You cannot use plasma as define it or even qualify it as a state of matter, okay? Yeah. State is a static concept. There's no such thing as state in two frames of the movie.
I think we can all agree about that.
Okay, so state is a static concept. Plasma is not. So here, let me show you.
By that definition, would color be a state?
Well, let's look at this. Here we have it. Here we have the different states of matter: solid, liquid, and gas. None of those three require motion.
You got a GIF here. Can we get the ionized? Can I get the ionizing in a picture?
See, we have solid, liquid, and gas. The words, right? There's no such physical object called solid. Solid is a category. There are many solids. So solid is a category. So is liquid. So is gas. But ionizing is something that involves motion. It cannot be a state. You cannot say plasma, the fourth state of matter. No, state, there's only three states. And those are solid, liquid, and gas, because those three words do not embody motion. Whereas the word plasma does embody motion, so plasma is not a state. And I know that destroys the religion of all people of the electric universe who also think that electricity is a physical object when electricity is something in motion. So it's a movie.
Where do you think the problem would be? Are you just seeing such discrepancies with the categorization that you're just convinced that at some point down the line of their presentation they're going to mess it up, or what?
Well, they do mess it up. They do mess it up because the electric universe says, for example, just an example here, gravity is electricity. Yeah. And they try to explain it with electricity. No, gravity cannot be electricity because you have to identify the physical object, the mediator of gravity. And you cannot say electricity is the mediator because electricity is something already in motion. You got to... Whatever you present, a tree, a dog, a line, whatever, it's got to be static. You got to show it and say that's what's going to serve as the mediator of gravity. You cannot say electricity because electricity is already in motion.
Well, what's wrong with something already being in motion?
Because
the universe is already in motion.
Because in physics, in science, right, the scientific method, you have to present the objects and the definitions first. First step, objects and definitions. And you have to point to the object so we know who are the actors. And this guy says, I'm going to present a boy running. Or a running boy. No, you get. Please present the boy. Then you can put him in motion. But please present the boy first.
Well, I'm sure they haven't broken down electricity to the minute level you have either. But are you saying that because they would have to also take electricity and say, okay, what is electricity? What is it that's moving?
Yeah.
So they don't do that. They still have to break down electricity into the static and the movement of the static.
In fact, it's even worse in the sense that they already know, quotations, what electricity is. Electricity is what quantum mechanics gave to the electric universe and to all these people who use electricity as a mediator. And that is, an electron beam moving from atom to atom. That's electricity according to the electric universe and according to the establishment. And so the question is, what is the object? Well, the object is the atom. And then you ionize it. In other words, you have that electron beam leave the atom, go to another atom, and it goes to another one, and that process is called electricity, according to the establishment.
I don't want to go too deep into this if you don't want to, but just as a quick last question, how would you conceptualize the pull of gravity? Are they saying that there's wires of atoms between everything?
No, that it gets even worse.
No, because I don't want to know.
No, you want to know. I want to let you know whether you like it or not. No, what they say is positive and negative.
Where are the atoms?
Don't worry about that. Because it's all conceptual. They say positive attracts
negative. Hold
on.
If electricity is an electron going from atom to atom, whatever an electron is, right? But that implies that there's rows of atoms.
And what you have is the electron. No, in fact, they got rid of the atom too. All they have is electrons moving now, without any.
Now we're just shooting guns.
Just shooting beads. So the electrons go from positive, towards a positive pole.
Yeah.
And
where's the pull?
I don't know.
You didn't do your homework.
It only goes one way.
Okay. I think I'm good on the electric universe.
Okay, another fellow goes in there and he says the following.
It's funny when I need you to explain crazy theories as if they're supposed to make sense.
Yeah, right. Here the fellow says Newton didn't base his gravity equation on anything static. Again, he based it on Kepler's laws, especially equal area swept at equal times. Okay, the point here is that this fellow doesn't understand what static means. Okay, and that's the whole issue here. So let's go with that. Let's find out why Newton's equation is static. Gravitational equation is static.
Yeah.
Okay, that's what we need to explain here. What do we mean by static when we say Newton's equation is static? Okay, and I'm going to give you two answers to that. One is related to distance, and the other one is related to weight. Okay, so here let's go with the first one. Okay, here let me get rid of this one here. I got rid of the wrong one.
Can't bring it back?
I guess not. It doesn't matter here. Really what it was the... maybe I can't get it back, but let's get this one. It doesn't matter here. Okay, so because this is essentially a breakdown of what I was going to say anyways.
Yeah.
On the left-hand side, what you have is the distance of physics, and on the right-hand side, you have the distance of mathematics. The distance of physics is the one embodied in his gravitational equation. Newton's it's attributed to Newton, so we're just going to use Newton as the reference. So the gravitational equation, Newton's gravitational equation, which you see the equation up there, that one's got a static distance. That's the distance of physics. That means there's separation between two objects, two masses. Okay? The one on the right is something totally different, which is Newton's second law of motion. Okay? And sometimes they say, well, we make the F on the left-hand side equal to the F on the right-hand side. Big error, because qualitatively they're not the same. And you can see there the differences between them. In the case of Newton's gravitational equation, you're talking about the distance between two objects. It's a static separation. Static. There's no motion. We don't count meters. We don't count centimeters. We don't use meters in physics. That's mathematics. And that's what you have on the right-hand side. The right-hand side, what you have is motion. And you're going to count how many meters the guy moved or the one object moved. The first one is between two objects. The second one, the one on the right, is a single object moving away from something or towards something. So we're looking at the motion of one object. And so we're talking about distance traveled by one object, not the separation between two objects. Okay? And that's what we have in Newton's second law there of motion. And you can see some of the differences there. So when I say that Newton's gravitational equation is static, I'm referring to the fact that that you're talking about a separation, a physical separation between two objects. Okay? And that's what we mean by static. And if you go down the line there, if you go to number 6, there it says distance is a measure of weight. Weight is a static concept. Okay, weight is a static concept. Why? Because you don't need to move. In fact, if you move in space anywhere, you change your weight. Okay, your weight changes instantaneously as soon as you take a single step. Okay, so never take a step because you're going to lose or gain weight. Okay, in physics. And of course, they could never answer why that is the case. Why? As soon as you move in space, why does your weight change? And here I'm going to illustrate that for you, okay? See if we can do this. Okay, astronaut farther away from the Earth weighs less. If we could weigh him out there, he'd probably weigh 25 kilograms. Closer by 50 kilograms, and down on Earth he probably weighs 100 kilograms.
Hey,
why?
You gave the 50-kilogram guy more ropes. That's cheating.
Yeah, more ropes. Why? Because he's closer to the Earth. Every rope in his body is from every atom in his body is connected to every atom on Earth. The closer he gets to the Earth, the more the ropes tug independently. So if you take that astronaut to infinity, so to speak, all the ropes come in together, and that's why gravity is so weak, because it acts like a single rope, like a single coaxial. As he gets closer and closer to the Earth, he has this acceleration, because the closer he is to Earth, the more ropes tug independently. They're not on the same axis. Okay, and that's what's happening. But for a given point in space, for a given distance, static distance, if I were to freeze that frame, the astronaut has a given weight. As soon as he moves an inch closer to the Earth, he weighs more. Okay, that's what it is. And so weight is a static concept because force in Newton's equation is a static concept because distance is a static concept.
Which is confusing
we're all
because...
static.
Well, the reason someone would think, in fact, even if someone asked me if weight were a static concept, I would have guessed no. Because if you put him on a scale,
he's got to push down.
Yeah, it's like the running boy, the weighed down man.
Okay, so let me point out to what you just said. Yeah. Okay, you step on the scale. Okay, as you press down, right, you're getting closer to the Earth. Your weight, the scale starts going up, right? Because as soon as you put one foot, it goes, 10 kilograms. But as soon as you put your whole weight, it goes up higher, right? Yeah. Because you're pressing down on the scale, you're closer to the center of the Earth, right? But once you stop, right? Once you stand absolutely still, hopefully you don't move in any direction.
Yeah.
If you could achieve that, at that point you have weight for that location only. As soon as you move a little bit to the side, whatever, your weight changed. Okay, so if you could stay absolutely still without moving anything, if you could do that, then you would have weight only for that location, because you have the same distance with respect to whatever other atoms are on Earth. Okay, another issue here. Fellow says, gravitational field is what the experiment of Cavendish proved. We talked about the Cavendish experiment the other day with the measuring of the value of the constant G. Okay, field is the space. Field is a space. Space I thought was nothing, but he says field is a space of the gravitational interaction between two bodies with mass. Furthermore, it could be the infinity of space. Space is infinite? What do you mean space is infinite? Is space a physical object or not? If it's a physical object, it's finite. And if it's infinite, it can't be an object, because an object is that which has shape. So he's got a contradiction saying infinity of space. No such monster in physics. Okay, again, these are words that they fed him in his brain and he just accepted it from the monastery. He's got to think that there can't be infinity of space. Either space is an object and is finite, or it ain't an object, in which case the word infinity doesn't even apply. Okay, it is space of interaction between two magnets, whatever that is, the space of interaction. Okay, it was proved by Maxwell. I like the fact that they prove. Proof means that someone convinced you.
We finished. He already proved it.
Yeah, no, but proof means that someone convinced you of something. That's all proof means. The word proof belongs to religion. In fact,
what I always say is proof is persuasion.
Yeah, it means that someone convinced you of something, and that's why you believe it, and it's proof to you, not to your neighbor.
Anytime you hear the word proof, just listen to the word persuasion.
Yeah, it means I want to win over you in the argument, so I say they proved it, and you're wrong.
It's creepy.
You should accept it.
It's a little disorienting when someone makes those two that comparison. That proof is persuasion, but it's like, I wish that weren't true. Because everyone likes the word proof. It's just, it's solid.
Because proof means that my religion is stronger than yours.
It means you can finally put a stake in the ground and I can build a house here. No, it's still wobbly. No, it's still persuasion. There's nothing.
Okay, another fellow says, a force is when an object moves. Okay, that's a force. An object moves because it interacts with another object or field. So we have a force interacting with a field. Great, we have two concepts, force with field. This one is called energy, another concept. And it's what makes things happen. Yeah, I guess. We have all these concepts interacting. See, this is the
force
problem.
Is when an object moves.
But see, this is the issue. The issue is that all these people are using concepts. Force, field, energy are all concepts, mathematical concepts, and they have them interacting. They say, the force interacts with the field and the field with the energy, or we call it energy. It's all concepts, mathematical concepts that have no place in physics. Physics, we have to explain the mechanism, why a pencil falls to the floor, so to speak.
It's a weird way of saying, of talking. It's like if I said, my field of view engulfed something.
Yeah,
it's
good poetry.
It's a weird way to talk when you're using these concepts, interacting with the world. No, your field of view didn't engulf the world.
But when you attack that, they say, you're doing word salad. You're attacking it from a semantic point of view. Well, yeah, because you're doing word salad if you're introducing concepts as objects. You're doing the word salad, not me. Okay, so here's another fellow. He says, light and magnetism are proof of the existence of electromagnetic ropes. Well, keep in mind that the rope is not something we prove, okay? We make an assumption. We make an assumption that there is a rope-like mechanism, a mediator between two atoms, okay? And with that, we're going to explain, okay, a mechanism. So we haven't proven the rope. We're not asking you to believe in the rope. We're saying, look, accept the rope in order to understand the theory founded upon it. Period. That's all we're saying. Okay, we're not saying believe in the rope and this you got to accept it, and we're not here to convince anyone. We're here to explain mechanisms using.
What's this understand? We really care that everyone understands the theory, and then after that we don't care.
Right.
And
everybody can reach their own.
But to understand the theory, you have to it's almost like plausible deniability, or whatever the term is, where you have to accept certain assumptions for a time. Like, okay, let's
to
assume,
understand the theory.
Yeah, just to understand. Like, let's okay. If you wanted to explain the hole in the window, okay, let's assume
a cat did it, went through the wall.
Could that explain this?
Right.
All the.
And that's the way physics should work. Okay. The following says actually it was Leibniz. Over 300 years ago, who thought that the Earth could have arisen from a sun. We were talking about the fact that Earth was a star. Okay,
and you put your stake in that.
And it says Jeffrey mentioned in one of his videos talking about one of the fellows who came up with this stellar metamorphosis, or claimed to have been the originator. No, he wasn't. It was Alexander Oparin. But this fellow says, look, Leibniz even beat Oparin. Okay, and if you look it up, there's the reference there, Conservapedia. Leibniz supposed the Earth to have been once a star. Okay, and he wrote that in several of his books. This is to say a molten body, an incandescent liquid, without explaining how it got into that state. Okay, what's the issue? The issue is that Leibniz, 300 years ago, he did not have all the information at his disposal what we have today of new ideas of how the sun works, how a star works. Okay, that's the first issue. So he had his ideas, and he said, it could have been a star, but he had no way. If we would have bring Leibniz today, he would not be able to justify those statements.
You're saying he just said it offhand, like
he kind of had an idea. He said, "Look, it probably was a star, but he would not be able to justify it in a way that you would understand how it got to the state where it is today." In fact, he thought it was a molten some kind of mold that's somehow hardened and turned into the Earth. Okay, but he would not be able to explain it in today's terms. So in that sense, I don't know if we can give Leibniz credit. We can probably give Oparin a little more credit, even though Oparin said it in 1926. And if you look at Oparin's statement, he also probably should not be given all the credit, because he also thought of it as a molten. He got that from the nebular hypothesis, where you have this cloud that condenses. And so he's also using that as a basis. But here we are 100 years later. I think we can do better than Oparin, okay? So this is the nebular hypothesis. Here you can see a little bit of illustration of that, okay? You have the sun, and you have the planets. And according to the nebular hypothesis, they were all gases just roaming around that somehow condensed through gravitational processes. But the main thing I want to point out is you can see all those little planets, or the little gases that are going to turn into planets. They're residual gases. The big gas is the sun, and the little gases are the ones that are going to turn into planets. And here you see our planet as one of those, okay? There's our little gas bulb, and it turns into our planet eventually. In other words, it condenses.
No, don't delete those. I might need those for a question I have.
Okay, I'll keep that one there. But see, you can see what's happening. The little cloud there, that's going to be the Earth. Okay, one of those, or any of those, are going to be planets. Okay?
Yeah.
And I just want you to focus on that, because we have a different theory. Okay, that I'm going to tell you about it right now. You can see this turns into the Earth. Okay? Okay, so that was the notion that they had. What are we saying instead? We're saying that if we looked at the gases, the way we think happened, the condensation, the Earth was a much bigger cloud than the sun. Why? Because in order to make iron, Earth apparently has iron in its center, it had to be a much bigger gas cloud and a much bigger sun that eventually crushed or compressed hydrogen into helium and higher elements, and eventually into iron. Our sun cannot produce iron according to the calculations. So they say in order to produce iron, you need a much bigger sun than a much bigger star than our sun.
But aren't we still using the nebular hypothesis?
We are, but then the question is whether the gas cloud that made the Earth was the same gas cloud that made the sun. That's one issue. whether there was a gas cloud millions of years or billions of years before the one that made the sun, and that was our Earth in this vicinity. It condensed, it created our Earth, it was a star, then that star condensed into a planet, what is known as a black dwarf, and eventually there was another gas cloud which turned into a sun, and our Earth was in the vicinity and was captured and it started rolling around. So this is what I'm going to show you here, the sizes of the different gas clouds, the three gas clouds that I can compare them in size. Here it is, okay? I'm saying Jupiter, small gas cloud, and it condensed into what is Jupiter today, which is a star that never ignited because it doesn't have the mass to ignite. The sun was a bigger cloud, but it was not big enough to make iron. There was not enough matter to compress it so that it condenses the center into iron. The Earth had to be a much bigger cloud if it's going to crush all the atoms or crunch them so that it compresses them into iron. So that's in general what I'm suggesting. Okay, that's a proposal, and we can add to this what is known as the iron catastrophe. Okay, and that is that when a supernova exploded nearby somewhere, maybe it threw some iron or some heavier elements like uranium or even radon or whatever into our neighborhood, and that's why we find it still in our neighborhood. We find these elements on Earth, and this is more or less what the iron catastrophe is all about. It says, look, you've got this planet, and it was in a molten state, okay? And so what happened was that a lot of those elements, heavier elements, sank to the center, okay? There was iron crushing, banging against other iron. Some of that fell into the Earth and then fell into the center of the Earth. That's another proposal. I don't buy too much into the iron catastrophe only because there had to be quite a bit of iron floating around. And I don't think that's how the iron got into the center of the Earth. I think the way it got in there is that the Earth was a star and crunched it on its own, crunched the hydrogen to helium into higher elements, silicon, etc., all the way to iron. And then, yes, you can produce a center that is iron. And that would also explain why the Earth is differentiated. In fact, I'm saying that any round object in the solar system, right? Any round object, any spherical object, except the flat Earth, right? Any of those was a star of some kind. And in the case of smaller ones, like, little pebbles like, Mercury even, or the moon, I think they were the size maybe of Jupiter, maybe a little bigger.
But those ignited or did?
No, I don't think they ignited. I think that's why they don't have any gases on their surface. No, they have no surface. Yeah, they are, but they don't have gases on their surface, which would indicate that maybe they were not big enough or over the centuries, gazillions of years, they lost their atmosphere.
Even if they don't ignite, I'm sure just by the way the gravity works on these celestial bodies, that differentiation seems like an inevitability.
Yeah.
Eventually, just with enough time, you're gonna have those layers.
In fact, when Jeff pointed this out some time ago, 2, 3, 4 years ago, I can't remember now when, but I liked the theory. For the first time in my life, I came in contact with this theory. Finally found out it wasn't Jeff's, but Oparin's. He already had said it. And I was able to explain two things I could not explain since the days of high school, and that is why they're round and why they're differentiated. Mm-hmm. And round and differentiated, that's a star. So the Earth was a star that turned into a cinder known as a black dwarf. That's the way I look at it.
Did I hear you right? You don't think uranium and these heavier elements were made on Earth?
I'm not sure about that, because there's another problem with that, and you should keep this in mind for anyone who wants to tackle the problem, and that is you find all this stuff on the surface. The question is, how did it get on the surface of the Earth? Okay, now was that brought in by some asteroid?
But you find iron on the surface too.
Yeah. Also, but see, not in the quantities that you would find in the center of the Earth.
Obviously.
So there
you
could
still
be other
find chunks of it. So it's not perfectly differentiated. Let's put it like that.
The Earth is differentiated and quite perfectly differentiated. The question is, why do we find some of these elements that should not be on the surface? Why do we find them on the surface? And was that brought in by asteroids or comets or whatever?
Is it that the Earth is differentiated except the surface? Is the surface like the
that's where
wild card?
That's where the iron catastrophe comes in. The iron catastrophe just says there was a lot of metal flying around because there was a supernova that threw all this garbage into our neighborhood. And here was the Earth, or the sun, condense our star, right? It was condensing, and at some point, maybe a lot of this garbage fell in there and just ended up on the surface of this cool star that was trying to cool in its last moments. And that's why it's still on the surface or somewhere on the surface. Maybe some of it was still in a molten state or in a gaseous state, and some of that penetrated a little deeper. So if we go, a kilometer down the Earth, we'll find some iron, some...
Hold on, does it have to be so complicated? If there's tectonic activity and there's volcanoes,
could bring it from the surface.
That's what I'm saying.
So there's a lot of processes you can consider.
There's a lot of motion on our rocks that's sending stuff from the bottom to the top.
Well, the point here is there's a lot of theories that you could implement. Say, well, why is it here? Well, because of this theory. Why is this that? Because another one. My general point is that all these round objects had to be some kind of gas that condensed and turned them into a star. And it could not have been the same gas that made the sun, because the Earth had to be a much bigger gas cloud than the sun when it formed many billions of years before our sun. The Earth was there when the sun picked it up.
Yeah, but the Earth already shed its husk, which is a lot of gas, to make the sun. So the sun right now is using what the Earth shed off.
It could be some of that gas that from our surface. Well, I'm sure a lot of it is, but I can't say that the big gas cloud that made the sun came all from the Earth.
Maybe. Where else would it have come from?
Well, it could have been a supernova exploded through that gas or that garbage into our neighborhood when the Earth was still rolling around, in the middle of nowhere. So, the point is, there's a lot of theories to put in there. I don't buy the nebular hypothesis for the planets. It is for the sun, and it would be for the Earth when it first formed. But what I'm saying, the Earth must have formed before the sun. The Earth was a captured black dwarf. The sun was the last member of our solar system. That's my point. Okay, let's move on here. Anyways, all those are theories for you to consider.
I had one more question.
Okay. Let's see. What you got there?
Because the way I conceptualize our solar system is, since other solar systems are so far away, we're almost like a contained unit. When you talk about...
Self-contained.
Yeah, self-contained. Because I almost have this notion, not a theory, but this notion that there's no such thing as a supernova flinging matter from one solar system to another. That's almost impossible because they're just so far away. Well, you even talk about the bird's beak and stuff like that.
Okay, but you have novas and supernovas, and I can imagine that when they shed all that skin, that's a lot of
across solar systems too, like between galaxy kind of stuff.
Well, for us, the distance from here to the nearest star is a long ways away. Yeah. But for a galaxy or for a star, that's just a couple meters away. In a sense. So you have to remember one thing. Another one is that the magnetic field of our star, of our sun, extends way beyond Pluto. So, and you say, Pluto's out there in the middle of nowhere. It takes hundreds of years to get there, for the sun. It's got its magnetic field around that and beyond.
Because I was wondering, assuming our solar system were self-contained, and assuming you can't turn matter into nothing into matter, the basic assumption of our whole thing, then would that imply that our solar system repeats over time?
What do you mean repeats?
Well, because if the sun explodes, scatters, matter all over, then the nebular hypothesis starts again. You start convening to make a new sun. Yeah. Like, if the sun explodes and destroys the Earth, you're going to have all this just kind of matter floating around in our solar system. Then it's going to start the process all over again of reconvening into the Earth sun. Yeah. That's going to turn into a black star. And then our now sun will... black dwarf, Then our now sun will come after that. Is it just like...
in other words, now the sun becomes a planet.
Yeah, but is it just a repeating process?
I think to some degree it is, and maybe you can pitch in there, supernovas that could be throwing garbage also into the neighborhood. So, all I'm saying is we have to look at all these theories and put them all together. We can't just go with the nebular hypothesis and say, oh yeah, there was a cloud, and a big cloud was the sun, and the little clouds was the earth. I don't think that works. I think if you're going to do this, you're going to have to look at a lot more variation. You're going to have to include stuff like the iron catastrophe could have happened, supernovas throwing garbage into our neighborhood, molten state where comets and asteroids bring garbage into your planet and what's going to become the planet. I think we got to look at all these processes and try to, get a better idea of how our solar system was really formed.
Well, yeah, I asked because one of the most interesting topics to me is the repeatability of the universe. Assuming there is no, beginning frame or ending frame.
Right.
If it's just kind of eternally there, then you almost have to, at some point, explain the whole. I don't want to say life cycle, but like universe cycle. Like, how is it that this wasn't the first Earth?
It wasn't the first universe.
I
think that it's an ongoing process.
But it's fun to explain that whole process because it isn't linear.
No, of course not. It's like cyclical.
Human history on Earth is linear, but the universe, the way it kind of recycles itself, isn't. And it's just always interesting to me. How is it that when the sun explodes, that a new Earth is made?
Well, even worse, like I say, there never was a first human being in the universe. Yeah. Because when you go farther back in the past, there had to be some human somewhere in the universe. And if you go 1,000,000 years in the past, there had to be some human somewhere in the universe.
It gets really sci-fi.
And when you start to think of it, if matter cannot turn into space and space cannot turn into matter, the universe has always been there, and there was never a first human being. We always have this thing about origin, starting. You're born. That doesn't happen with the Father Universe. He was always there.
He's still going.
And we don't understand that.
It's weird.
It's very hard.
The way I always explain it to myself, if we were once, that means we will always be.
Yeah.
It's one of those weird sci-fi things.
And some human will come after us. Somewhere in the
universe. It gets trippy and weird.
Okay, a couple more issues here. One fellow says, Bill says the black stuff is space. This is irrational. The black stuff is the ether. Well, he hasn't told us what the ether is. He just says the black stuff. I guess he's referring to space, right? And black stuff is not stuff. That stuff that you say is black, that's known as space, and space is not a thing. So it's not stuff. Okay, so again, you have to tell us what the ether is. And unless you can define the ether or point to it, one of the two, either it's a concept and you define it, or it's a thing and you point to it and say that's the ether. You got to show us some kind of shape, a drawing, a picture, a photograph, a
mock-up. Isn't it always a sea of balls?
Huh?
Isn't the ether always drawn as a sea of balls?
I don't care. They can draw it as a ball, but then you got to tell me what's outside the ball, giving it shape. Okay, that's the tricky part.
Can't win with you.
Okay, so here we have another fellow also brings up the ether, and he says, I'd really like to know whoever said the ether was made of particles. That was me. Okay?
Yeah, well, everyone said that.
Ether being particles is complete nonsense, okay? The only ones I know of the electric universe quacks, they think it's made of imaginary neutrino.
What else could the ether be if not balls?
Well, this is the issue. The issue is, this fellow you can see as all ether is. The all ether is. How do we define an ether is? Here, let me define ether is for you, and that'll tell you everything. An ether is a person who cannot define the word ether or tell you what it is. Yeah. That's what an ether is. Never has an etherist who came to this channel ever been able to define the word ether or point to it. Put a picture and say, look, here's the ether over here. Look at it and tell, and now you'll know what the ether is. It doesn't mean the true, genuine, super duper ether. It's the ether he's got in his brain. Yeah.
How does he conceptualize it?
Yeah, I need to know how he conceptualizes it.
Because I would like to conceptualize it as well in that matter. So, I mean, even just to understand it. Like, is it a sea of balls?
We cannot guess what you have in your brains. If you're going to present the ether, first of all, you have to decide whether it's a concept or an object. If it's a concept, define it. Tell me what the meaning of the word ether is according to you. If you think it's an object, draw it, put a picture on the internet and say, look, Bill, there's the ether. Okay? And of course, if you put a shape, you got to tell me what's on the background, because a lot of people, like this fellow says, the ether is space. Okay, but space is not stuff.
Well, that's the thing. According, there's a very low chance that we mean the same thing when we use the word space. When he says space, we understand nothing.
Yeah,
nothing. So but in his mind, he's got something else.
Okay, then put it there. If you think it's a thing, just draw it and tell us what is the background that gives it shape.
You want to backdoor the space at any cost.
Okay, let's continue here. We got a couple issues. Well, let's. We're gonna skip over this. I'll probably treat it next time. We're gonna move into the subject matter of today, which is.
Oh, we didn't start yet.
Yeah, we haven't started yet. Dark energy, and as some of this serves as a background, because a lot of the problem with dark energy, right, has to do with language, has to do with people not defining their terms or using concepts as physical objects. And that's where we draw the line. We have to stop them there and say, look, concepts are over here, objects are over there. Every word in the dictionary falls under one of those two categories. Objects we can point to and name and say that's it. And it's an object, it's got shape. And concepts, first, don't have shape, and you must define them.
I was telling him yesterday that what he does in a lot of ways is very much like coding or programming, because you have to define your variables rigorously. You have to have a very
the computer needs to understand it.
You need very clear definitions, whether it's a number you're talking about or a word you're talking about, or what category it's in. It's very, very rigorous. Like you can't cheat, or else the computer will not understand you.
Yeah,
but the thing is, with humans, you can get away with murder because we're very poetic. since we can kind of I see what you're saying.
Yeah, that's one of the issues that we do a lot of poetry, especially people who want to do physics. Yeah. That's one of the problems. The other issue is that
the running boy fell sounds like a normal thing to us.
A lot of people got used to using the language that they were taught in high school, especially, right?
Well,
and they never questioned, how we're using concepts as physical objects. I mean, you look at any textbook of physics, and where does it start? It starts by telling you about concepts. This is force, okay? And this is mass, and this is acceleration. All those are concepts. Physics is about object. You can't do physics without an object. So the first thing you have to define is the word object, and not a single textbook of physics on planet Earth ever defined the word object. But a thing is.
I just think it's very interesting how you got very programmery with your physics.
And I was going to say about
that's
that.
When you get into real nitty gritty.
Okay, and I wanted to say about that. In a computer, if you don't program, what you were saying now, if you don't program the word in the right way, the program doesn't know what to do. Yeah. There you have to be very specific, very objective.
It's worse. Yeah. You won't know what you meant. That's what I was trying to tell you.
Well, I care about the ChatGPT. He doesn't know that we're in trouble.
But it comes back to the just understanding physics in general. Yeah. If I'm reading my own codes sometimes and I've named a variable in a way that I don't understand, I won't know what I meant 2 months ago, which adds to all the confusion. Where I'm like, okay, what did I mean? Like, forget if I believe whatever. Just understanding what is on paper is hard because the variables are all.
Okay,
misnamed.
So let's get on with dark energy, and for this we have to understand how this thing started, more or less. Okay, it starts with the Big Bang. That's relativity's version of how our universe began. We said a minute ago that the universe never began; it's always been there. Mathematics has reached a different conclusion. They said, look, there was an explosion 14 billion years ago. Some call it an explosion. Other people don't like the word explosion, but that's why they say it's not really an explosion, and it's a long story.
It goes, woof. What else is that?
They say it's not a hand grenade, that just exploded. Okay. But it is. It ain't, but it is. Okay, and here it is. This is the way they visualize it.
A bunch of stuff flying out of an epicenter.
We had this, okay, there was this explosion.
Yeah, that's not an explosion. That's just a very...
That's a hand grenade that exploded, throwing all this debris.
That's quick expansion. That's
and
not
the first dot that you see, just as soon as it appears, that's known as the singularity. How that singularity got there, they say, well, that's an unscientific question because we have no way of verifying or testing or whatever. Okay, so what the religious people will do is say, hey, we agree with you, but you forgot to put God in the picture.
Yeah,
God created
God
the
was
singularity.
one frame before that.
Right.
Very easy.
But see, the so-called scientists, the mathematicians, they don't like it. Okay, so what happened?
You just missed them. God just came by.
So we had this explosion, okay? And this is what happens. This is the sideways view of this. It explodes and it builds this little cup, this little glass, tilted glass, right? And what you're seeing there, each one of those lines, that's time, okay? So you can see that the explosion led to this time thingy. And that last one, the W map there, that's covering the end of the cup, that's our present state. In other words, that's a cross section of time, and we're all living on that flat universe, as they call it, because they believe in the flat universe.
So not flat Earth, but flat
no,
universe.
they're not flat.
We've
Earth.
upgraded.
Are you crazy? No, it's a flat universe.
We've upgraded.
So we live on that flat universe, okay? But then what they do is they show it in this way, okay, because you have to visualize it in this direction for us to understand it in our 3D world. And it's like this, okay? You're supposed to see it like that. Our universe is a ball that is exploding. It's a balloon that's inflating, okay? And as you can see, all the galaxies there are flying apart. And the little curlicues, that's light. The light is being stretched as the universe expands. And of course, people have one question usually, and they say, well, what's the white stuff that gives shape to the ball? And that's when they say, well, it's an unreasonable question. It's an unscientific question because on the one hand, the universe is not expanding into anything. That's one answer that you get. And the other one is, well, we don't know, and we have no way of proving it.
Well, wait, hold on. We got the gray stuff that's expanding, but what's also the white stuff of the backdrop?
We
have two questions.
But that's the question. Well, the gray stuff is space. That's why the white stuff is not space.
Okay, so white stuff is the gray stuff is space.
Yeah, we know that what space is. That's a gray stuff that's expanding. Really, it's not space. Sorry, I will qualify that. It's space time.
That's even worse.
Okay, it's a space time. This is a 3D version of our 4D universe. Okay, so it's you're supposed to imagine it in 4D if you can, and we don't know what the white stuff is. Maybe it's the 5th dimension, 10th dimension.
What are the yellow dots?
And the yellow dots, you can think of those as stars or galaxies, and the curlicues are light going from one galaxy to the next. Okay. As the universe expands, it stretches light, the wavelength of light. Okay.
Does that mean that light?
And that's why all the galaxies are red shifted, meaning they're receding from us because light takes longer and longer to get our.
But worse, keep that gift there. Does this mean that light doesn't
travel at the same speed or what?
Something like that, because the distance is getting.
Yeah, but remember,
you know what I mean?
No, but remember the issue. The issue here is that
if I'm running away from you and I turn a light on, there's more distance for the light to travel.
Not for light, because Einstein said light always travels at the same speed.
Yeah, okay.
No, but hold it. You got to understand it. That's where the equation comes in. Little c, 300,000 kilometers per second, is equal to wavelength times frequency. Meaning, when the frequency goes up, wavelength goes down, and vice versa. That means all you're doing is stretching the wavelength, but that means now you have a lower frequency.
But the light is still taking longer to get.
Not
because it's traveling slower, but the distance is getting bigger.
Yeah, but that's why they're saying that all these galaxies, we'll never get to them because they're flying away faster than light, or even faster than light. Yeah. Because the universe is ballooning faster than light can travel. That's the.
Wouldn't that mean that they're just standing in place? If the balloon gets bigger faster than light, then we shouldn't be able to even see any other galaxies.
Yeah, but
the light never gets to us.
Yeah. Of the distant ones, yeah. The ones that are closer by, they're not as faster than light. But the ones distant that are farther away from us,
some regions are getting further away faster than other regions?
The farther a galaxy is from us, the faster it's receding from us.
Okay.
So the ones closer, we can see those, but the day will come when we can't see those either.
Jesus.
Okay, so who came up with all this stuff? Well, here we have our three heroes: George Lemaitre, Albert Einstein, and Edwin Hubble. Edwin Hubble was an astronomer. He looked there. He said, "Hey, all the galaxies are receding. They're all redshifted." And George Lemaitre essentially said that he came up with this Big Bang notion. Albert Einstein never believed in the Big Bang theory. Okay, some people dispute that, so there's still, I guess, the jury is still out. But good old Albert, he did not approve of a lot of stuff that they made of his theory. He never believed in quantum mechanics. He didn't believe in black holes. In fact, he did talk about that. He wrote papers against that. He didn't believe in gravitational waves. And there's a fight of whether he believed in Big Bang or not. I take the position that I haven't found evidence, in his writings that he actually believed in Big Bang theory.
Do you think all the physicists were just kind of waiting until he died so that they can put a bunch of words in his mouth? You know what else he said? He thought my theory was true too.
They made a hero of him.
Yeah, but it's like they're waiting. Come on, I need you to die so that we can fill your mouth with a bunch of words.
They made him a reluctant leader of the movement. Okay, because Einstein died a broken man in intellectual terms. He never could figure out the grand unified theory. So he was a little frustrated that he died 1955 before he could figure that out.
I think a lot of people are
But he disagreed with a lot of stuff that everybody that came around him or after him, he disagreed with a lot of their stuff. But he couldn't do anything about him. They say, "Hey, you're our hero."
That guy's rolling around in his grave right now. Stop, please.
Okay, so here we talked a little bit the other day about this, which is Einstein's gravitational constant there. And we're not interested in all these little letters and variables and so on. We're just interested in one thing, and that's the cosmological constant. Okay, and that's that lambda g sub mu v. Okay. What's the issue? That, by the way, that's a tensor, and a tensor is simply a different version of a scalar, which is a vector is a complex scalar, a matrix is a complex vector, and a tensor is just a complex matrix. It's just a more sophisticated matrix. People understand more or less what a matrix is. Tensor is the same thing. That's why you have the 1, 2, 3, 2, 1, 7, 5, 4, because that's what the mu v represents. But we're not interested in all this stuff. We want to understand what this means.
We're just talking about a position on a graph?
No.
Is that what these are?
Yeah, no, it's just, see, because this is an equation that represents many equations, okay? So you got to look at it like that. But what we're interested in here is what does this mean in physical terms? And the one I want you to focus on is the cosmological constant, which Einstein had quite a bit of trouble in. He put it in, he took it out, he put it in, he took it out. He didn't know what to do with the
playing with it.
Cosmological constant. And the important thing there is, first of all, that is the variable in this equation that represents dark energy today. And I want to focus on the word constant. I want you to see that it is a constant, okay? I want you to keep that in mind throughout the chat today, okay? It's a constant.
The G is a constant.
Yeah, the lambda is a constant, okay? The whole thing, this cosmological constant is a constant, okay? Hopefully people know what constant is.
It's a collection of...
Well, no, constant means it doesn't vary. There's no variable.
But the tensor is...
it's treated as a constant. Okay?
And a tensor is a collection of...
It's a matrix. Again, the best way to visualize a matrix, people more or less understand the word matrix. Tensor is just a matrix, okay? Just a more sophisticated one. But this is the point. Here we have it, okay? This dark energy is supposed to be the stuff that's pushing everything outwards.
The red stuff.
Okay? Yeah. It's the expansion of space and time. Okay? Important to include time in there. But then the question is, what's the black stuff it's pushing against? Okay, that's important. And of course they say, well, that black stuff that's around it against which it's pushing. We don't know what that is, or it's an irrational question or unscientific question because we have no way of proving it through an experiment, blah, blah, blah. Okay, so that's the answer to that. Okay, so that's what we're talking about. We're talking about the expansion of space-time. That's what you're staring at there, okay?
I wish you could do that in court. That's an unscientific question. Objection.
Okay, what's the problem with that? Well, all the galaxies are receding. You know, they're all redshifted according to the establishment, and redshifted means that something is going farther and farther away from you. If it was approaching you, it would be blue shifted. It's like the Doppler effect, you know. The train approaches you think, and when it passes you, you know, and so the lower pitch, that means it's receding, and that's what they're saying happens with light. We have a little problem with that, and the problem is that the local group, the galaxy which are in our vicinity, there's like 54 now. There used to be like 20. Now they found like 54 of them. They're all blue shifted.
Uh-oh.
And they're coming towards us. And so the question is, hold it, you have this balloon, right? It's expanding, all galaxies should be receding, but the ones in the local group are coming towards us. They're blue shifted.
How do they explain that?
Well, yeah, it's easy to explain.
Don't tell me an unscientific question. Come on.
No, it is a scientific question.
Okay.
They have a scientific answer. The answer is that gravitational forces and electromagnetic forces are overcoming the expansion of caused by dark energy. So dark energy does its as much as it can to push everything apart, but gravity, fortunately, whatever that is, and electromagnetism, whatever that is, are bringing everything in the vicinity closer together because they're too close to us. And the question is here, are they that close? I mean, you talk about Andromeda galaxy, right? And Andromeda is 2.2 million light years away. That's close enough for gravity to be pulling and electromagnetism to be pulling and overcoming dark energy, which is doing its best to push everything apart. You know, so you got to think about that. And so here, I just wanted to point out, here's good old Andromeda, okay, that's what it looks like, and it's that's a big picture of it, but really it looks like a little dot in the sky. And you say, well, that's so far away. How come that one's not being pushed by all that dark energy that's pushing everything farther away? And remember, that galaxy that you're staring at there is bigger than the Milky Way. Okay, so and these are the two biggest galaxies in our vicinity. The
what's the furthest?
Andromeda is the biggest one, and the second biggest one is the Milky Way.
What's the furthest blue shifted galaxy?
Well, the as far as I know, I don't know the answer to that, but as far as I know, only the ones in the local group are blue shifted. But I don't know if they found. I guess they found no other one because all the other ones are red shifted or farther away. And the question is whether their assessment is correct.
Yeah.
And let me give you a different version of that so that for you to consider. Okay, it's based on the rope model. If you take a rope, okay, any rope, and you string it across from one tree in the forest to another one far away, 2 kilometers away, okay? And you make it as tight as possible. You just, whatever means you have for making it tight. You will note that closer to the ends, the links are shorter. And as you get to the center of the rope, to that whole space there, if you get to the center, the links are a little longer, okay? And that's all I want to show you. It's known as tired light. Okay? The phenomenon is known as tired light.
It'd be hard to see it with a good rope, though.
And there you have it. Okay, so you have two galaxies. Closer to the galaxies, you have high frequency, and the links are shorter. But as you get to the center between them, you would expect and here's exaggerated, but the point here is the links should get longer and longer. That means that if we're receiving signals from that center, they would be red-shifted. That doesn't mean that the galaxy is receding. It just means that we're staring at part of the rope that is red-shifted.
Yeah, so you're saying it's just far away doesn't mean going away.
Correct. It just means that the rope towards the center is going to look like red-shifted. And in the case of galaxies which are in our vicinity, well, they're blue shifted because they are coming towards us because of gravity. So I don't doubt that the ones close by are coming towards us and are blue shifted. It doesn't imply that the ones farther away are red shifted, meaning they are red shifted, but it doesn't mean that red shift means that they're running away from us.
Well, technically, blue shift also wouldn't mean that they're coming towards us. It could just mean that the light that they're giving off is intense enough in frequency that it just doesn't get tired by the time it gets to us.
My point is that there are other versions. Mm-hmm. That doesn't mean that the universe is expanding. And then you have the question of, what do you mean, the universe?
Oh, yeah.
There's no such thing as the universe. A universe is a concept because it involves a relation between space and matter. That's what universe means, space and matter. Yeah. So there's two thingies there, and it can't be a thing then.
Which one's getting...
And aside from the fact that you cannot make a picture of the universe because the universe is space and space is not a thing, therefore
can't take a picture.
It can't take a picture of that. It's nothing. It's that which doesn't have shape. That's what space is. So you can take a picture of all the matter if you had God's camera. You'd stay
all
far
the matter
away
going away from each other.
Yeah,
makes more
but
sense.
you cannot take a picture of space. Sorry, and so space cannot be expanding, but it's not a thing. Okay. But then what happens? According to the establishment, we have this issue where you have gravity warping time, space-time, right? And what you're doing, not only warping space, you're warping time, because time is part of space-time. It's this structure, 4D structure, unimaginable 4D structure that they use in mathematics to try to not explain, but describe mathematically how gravity works. And so they say you have a mass, in this case the sun, weighing down this 4D canvas, which is made of space and time, three dimensions, as they call it, which are not dimensions, and time dimension. None of them are dimensions. They're all number lines, okay, because they're talking about math and about physics. But they warp them, and they say this is what causes the warpage of space-time. And because space-time is warped, then the Earth rolls around like the little ball on a roulette. Okay, that's why it can't fly away from from the sun, from the solar system. But then the question, if that's space and time, what is the black stuff that gives contrast to the net? And of course, they never answer that question. They say, well, it's an irrational question.
There's a lot more problems with it.
You're not supposed to take it literally, the analogy.
There's a lot of problems with that. Why aren't people being crushed? Why can people go to the moon? There's a lot of...
But I think the main one here is that, that you're warping time. That's what I want you to focus on, because we're talking about dark energy. And so we have two issues here. The first one is that gravity is the warpage of time. Let's forget about space for a second. We're going to warp time, right? Okay. That's what we're doing with gravity. But then we have dark energy, and that's pushing everything apart, okay? Yeah. And what did we say at the beginning? We said we have this explosion, and this time is, expanding out there, and that's what's pushing, the galaxies and the stars and the planets apart. Okay. So we have two things. We have a planet, a mass, right, weighing down space-time, and then we have space-time, let's forget about space, time also pushing, expanding, because you had that balloon, right, it was pushing everything apart. That's time expanding there. So time doesn't only warp, time also expands. It's getting it's bloating. Yeah. Okay? And so
I never thought about that.
Here we have one aspect of that. That's the time bending. That's one aspect that they want to give you. Okay, but then it's doing this as well. It's also expanding while it bends.
Lego says they can't draw it. You just put the word time.
Yeah. It's bending time, but at the same time that time bends, it's also expanding. So time. Time is doing two things, so keep that in mind. It's very dangerous. I mean,
that's stupid. You have to just write the word time because they don't have a picture.
Okay, so I hope you understand what's happening here. Not only is time being used to explain gravity, which is really the opposite of what they're talking about, because they say dark matter causes gravity. Why? Because it weighs down space-time. So now you're bending time locally. But then you have this time thingy, which is expanding, pushing everything apart, which is against gravity. So the anti-gravity is dark energy. It's made of time, right? But at the same time, it's also part of gravity, which is what is bending to explain gravity locally or in our neighborhood.
I need more shots.
But now let's throw in there a couple more problems with that. The first one is that, what did I say at the beginning? That cosmological constant was dark energy. It's a constant.
Yeah.
But time is not constant. So there's a contradiction because dark energy is this expanding time, which is variable, and they're talking about because it's expanding and bending and doing all this good stuff, but the gravitational constant that they're using is a constant, meaning it doesn't vary.
But if I'm
going to add another one now.
But is it a number that's constant or a relation that's constant?
It's a variable.
The lambda g.
It's a component of Einstein's equation that is a constant.
But is it a relationship that's constant, or is it actual variables that's constant?
What do you mean a relationship?
Like, for example, E equals mc squared, that could be constant even though the variables are changing.
Yeah, if they all increase at the same time.
That's what I mean.
But here you have that whole unit,
like
which is supposed to be a constant because it's called a constant, but at the same time, it represents the dark energy, which is what these people are investigating mathematically and also the astronomers. But here you have a contradiction because in one instance they treat it as a constant, in another instance they say, well, this dark energy is pushing everything away, but that dark energy is what? Dark time, really, right? And so you have this expanding, this variable compared to a constant. But let me add one more in there.
Please.
Just to throw it in there.
I wasn't confused enough.
No, now you're going to be confused forever.
Yeah.
You have Heisenberg's uncertainty principle, or principle of indeterminacy, whichever way you want to call it. Okay, so you have this Heisenberg's uncertainty principle, which applies to quantum mechanics, which is the world of the small, right? But Heisenberg's uncertainty principle has two versions. One is that if you have the more you know about position, the less you know about motion, okay, about displacement. And the more you know about displacement, the less you know about position, which I like to say is the more the ball stands still, the less it moves, and the more it moves, the less it stands still.
No shit.
Okay, that's one aspect. But then there's another aspect. This is where you got to hold on to your bridges. Okay. The more you know about energy, the less you know about time, and the more you can measure time, the less you know about energy. And here we have dark energy being pushed everything aside, which is made of time. But here they're saying that the dark time is the same thing as the dark energy because energy is made of time in this gravitation, in this constant. In the constant. So you have two issues here. You have the world of quantum mechanics that says the more you can measure the energy, the less you can measure time, and vice versa. And here you have energy, which is made of time.
Done. You're done right there already.
We have a contradiction there between quantum mechanics and
time.
But then how do they plan to reconcile general relativity, which says this nonsense, to quantum mechanics, which is another nonsense?
Isn't that why they're never going to get to the gut?
You
said earlier that Einstein.
We're talking about it anymore.
You were saying that Einstein must have. He died intellectually bankrupt because he couldn't figure out the gut. But I think a lot of people are in that predicament right now. Like actual physicist quotations. Let's just say people who are interested in the subject who can't figure it out.
Yeah.
There's a lot of them.
But this is the problem. The problem is that you have all these astronomers, all these theoretical physicists, and they're working on these things.
And they're looking for nothing.
They're looking for dark energy and dark time. So
I need you to look for something that's invisible. Gotcha, boss. It's like Three Stooges or some shit.
More or less. So here's the conclusions for today, okay? We have conclusions. We have relativity. The universe is expanding. That's what relativity says, right? So here are some of the questions for you to ponder or ask people that are knowledgeable.
That's something I was going to ask you. Is there more dark energy being created every second?
Yeah, of course.
Even though it's a constant.
Yeah, and that's why time is expanding because we're creating more energy, more time as time goes by. And so
we're creating more time as time goes by. We're done. Okay.
It says, is matter exploding or dispersing, right? Is it matter that is separating like a hand grenade? Or is it space that is expanding, or both? And they say it's both, okay? So we have both.
So nothingness is getting bigger.
Yeah, then the other issue is redshift proof that galaxies are receding is blue shift proof that the nearby galaxies are overcoming dark energy and coming together. Is what's happening here is the redshift proof that everything is exploding, is blue shift proof that everything's coming together. And so these things have to be addressed, because right now all the theories are based on this red shift, blue shift thing. Then you have relativity, gravity, what is it? Warp time. That's what gravity is under relativity, warp time. And then, but gravity is also, gravity pushes inwards, because that's what gravity is, whether it's pushed or pulled. But they always have a push, because when you have that depression, why does it fall downwards into the hole? But the question is it pulling or pushing? So it doesn't matter. So they always have push gravity. And dark energy does the opposite, pushes outwards. So one pushes inwards, the other one pushes outward. They're against each other, right?
As an aside, I would love to see you interview a physicist. Just you interview them.
Okay, so here we have dark energy. What is that? It's the expansion of space-time, right? So let's forget about space for a second here. It's the expansion of time. Yeah. But the cosmological constant is constant. It doesn't expand. It's supposed to be constant. And but we're saying that it is, dark energy is actually expanding.
Dark energy has time in it. It's getting bigger.
So it can't be a constant on one hand and also be treated as something that expands or changes, right? Then you have Heisenberg's uncertainty principle, right? You can't simultaneously measure energy and time, right? You can't do both of them at the same time. So we have a problem, because energy, dark energy, is time. And so I'm suggesting, that maybe what we should do is call it dark time from now. We live in dark times.
We do. We live in dark times.
So we're living in very dark times, okay? And I haven't got to the extinction segment, but we'll do that next week. Jesus. Okay, folks. We have anything that people want to ask there? Maybe something interesting?
No, I was looking through it.
Yeah?
Didn't see anything that stood out. A lot of interesting
Okay, folks. What we'll do, we'll look through the questions that people made, and we'll answer them next time. Okay? We'll see you then. Bye-bye.
It's been fun.